Partial fractions are a big part of that because it takes big ugly things and separates them into small little things. And the idea of partial fractions actually comes from the sum or difference of these basic common rational expressions. So let's say we have 3 over x minus 2 plus 4 over x plus 3. Well, to combine them, you're going to need a common denominator. So what's missing on this side as a factor is this x plus 3, so you'd multiply top and bottom. This should be, a little bit of review. And what's missing on the right-hand side, we already have the x plus 3, so what's missing is this x minus 2, so you would multiply it top and bottom. So after you've done this, our expression then becomes, after distributing, 3x plus 9 plus 4x minus 8 all over the common denominator of x minus 2 and x plus 3. And then combining like terms, you get 7x plus 1 is over x minus 2 and x plus 3. Now that's the direction we're used to going. Adding two fractions together, coming up with one term rather than two separate terms. What partial fractions does is it starts here, does some work, and ends up back at the beginning, at this expression. So that's what our goal is to take this big ugly expression and separate it into its two pieces that it originally came from, if you want to think of it that way. Now there's different setups for each one of these. Setup number 1 is the easiest one. If you have an expression, some function, polynomial of course, over linear factors like x minus a, x minus b, then because they are linear, you're going to separate it as a constant, we'll call it a, big A, over x minus a, and we're going to add on the other fraction, which is b, some constant, over x minus b. And the goal is to solve for this a and solve for this big B, the big ones on the top. The little ones are given to us like 2 and 3. So this is one setup. Now remember, f of x is a polynomial. I just didn't want to write anything weird up there. The other possible setup, if they're a linear factor or any kind of factor squared, has this special setup. Let me write it as p of x for polynomial. So what if we have something like x minus a all squared? Well, to get all the possibilities out of this, the separation has to be a over the linear factor and then b over the linear factor squared. So anytime you have a square term, you have to write, or actually any power for that matter. For instance, if this was cubed, you'd write x minus a squared, x minus a all cubed, and have a, b, and c on the top. So it really depends on what kind of factor is underneath. The third possibility, oh, by the way, I forgot to say this, the polynomial on the top has to be a smaller degree than the polynomial on the top, the bottom, the denominator. So the degree down here is 2, so the degree of f of x has to be 1. Again, the degree down here is 2 after you square it all out, so p of x here has to have a degree of 1. So in this next example, if I have a p of x, a polynomial function on the top, could be a constant, and I write a quadratic down here, then that allows p of x to have a degree of 1 also. And if there's another factor, then it could go up to 2, like if this was multiplied by x minus c. Then the degree on the bottom would be 3, and p of x could have a degree of 2. Now if the degrees are exactly the same, or p of x is higher, you can use long division or synthetic division to break it down until the polynomial on the top is smaller than the polynomial on the bottom, degree-wise. Alright, so if we have this setup, we're going to get a over the linear factor, x minus c, but when we get to the quadratic, like I said, it has to be a degree less than the one on the bottom. Because the degree on the bottom is 2, then the degree on the top's maximum can be 3. 3 can be 1. So what that leaves us is a linear factor bx plus capital C. So when you have a quadratic, you have to have a bx plus c. If this was a cube, you could have bx squared plus cx plus d, and so forth and so on. Alright, so the last possible weirdness you can get out of this is probably the hardest one, and I probably would never ever do this, is if I had a polynomial over a quadratic. Oh, let's even make it cubed, make it really bad. So this would turn out to be over x squared plus a and over x squared plus a all squared and over x squared plus a all cubed. And each one of these, since they're a quadratic factor, you would have to have a linear factor for the first one, a linear factor for the second one, and a linear factor for the third one. So let's see here, a, b, c, d, e, x plus f. This would be horrible to even try to solve. But that's basically the setup. If you have a linear factor in the bottom, you just put a constant in the top. If you have a quadratic in the bottom, you put a linear in the top. If you have anything higher than a quadratic, you have to go 1 degree below on the top. And if you have powers, you have to copy over the powers until you build it up to the maximum one. So here's a power of 1, power of 2, power of 3, and the exact same thing has to go in the top. If it's quadratic, it's linear. If it's linear, it's a constant. Alright, so that's our basic setup for partial fractions. Now how do we solve them? That's more fun. So let's say we have this, oops, not that one. Not that one. That one, there we go. Let's say we have a nice simple fraction to break down. So the first step is to factor the bottom if it's not already factored. So here we have factors of 3 that add up to 4, so this would be x minus 3 and x minus 1. So on the other side, if we're going to use partial fractions, it'll be a over the first linear factor plus b over the second linear factor. And our goal is to solve for capital A and capital B. So the first step is get rid of all the denominators. So you're going to multiply both sides by these two factors. And that makes life kind of easy. When you multiply this side by those two factors, they go away, and you're left with x minus 5. When you multiply a over x minus 3 times those two factors, the x minus 3's are going to cancel, and you're left with a times a factor of x minus 1. And then finally we get over here to b. When we multiply by these two over here, the x minus 1's are going to cancel, and you're left with an x minus 3 and that b. And after a few times, this is actually the easiest step of the whole process. Alright, now there's two ways of doing it from here, but I'm going to show you the long way because it works all the time. The shortcut doesn't. Alright, so let's distribute the a and the b through and see what happens. So you get ax minus a plus bx minus 3b. Alright, now there's a trick we're going to use, and it's actually a theorem. And it pretty much says this. If you have 3x squared minus 2x plus 1 is equal to ax squared plus bx plus c, then since polynomials are unique in nature, then the coefficients have to match up. In other words, a has to equal 3, b has to equal negative 2, and c has to equal positive 1. Otherwise, these polynomials would not be equal. So the trick is to use this idea over here, and what we're going to do is we're going to collect the x's, and we're going to collect the constants, and kind of put them together. So we get x minus 5 is equal to ax plus bx. Those would be your grouped x terms, and then whatever's left over is just going to be a constant. So we consider this negative a minus 3b as a constant, and over here this would be our degree 1 terms. Alright, so with the degree 1 terms we can factor out the x and we'll have a plus b times x. So the coefficient of the x term has to be a plus b. But the coefficient of this x term is 1. So that leads us to the equation that a plus b must equal 1. And over here, the constant is negative a minus 3b, but on this side, the constant is negative 5. So we get this equation, negative a minus 3b has to equal negative 5. And we get this system of two equations and two unknowns to solve. And it's up to you. You can do substitution or you can do elimination. Personally, I like elimination. It's perfectly set up for it. If I just write this down here, just taking this equation and shoving it in the bottom there, we notice right away that the a's are going to disappear. So we don't have to do any manipulation. We're going to get negative 2b is equal to negative 4. Therefore, b is equal to 2 when you divide by negative 2. Now, if b is equal to 2, we can go back up to that equation and write in a plus b, which is 2, has to equal 1. So that means a has to equal negative 1. So here's what a is equal to, and here is what b is equal to. So we go back to the very beginning. Here's our expression that we're going to substitute into. It's equal to the original fraction over there, and we get negative 1 over x minus 3 plus positive 2 over x minus 1 must have originally, when you add them together, come up with x minus 5 over x squared minus 4x plus 3. Squeeze that in there. So that's what it is to be partial fractions. You take a fraction and rip it apart into its primal parts. All right, let's try another one. Let's see, this one. This is a different setup. It has that linear factor squared in the bottom, which is different than a quadratic. So when we split this one, we're going to do the x minus 4 twice. We're going to write it as a linear factor by itself, and then as the linear factor squared. All right, and then in the top, we just get a and b, and we need to solve for them again. All right, so same little trick applies. You're going to multiply through by the common denominator, which happens to be all of this. When you multiply it through, these will cancel itself out. You're left with 5x minus 19 is equal to, when this factor hits this fraction, one of the x minus 4s is going to go away, so you're going to be left with a and a factor of x minus 4. When this factor hits the fraction b over that x minus 4 squared, they're both going to cancel and you're just going to be left with b by itself. Now this is probably one of the easier types because, well, b's by itself. Alright, so if we expand, we're going to get 5x minus 19 is equal to ax minus 4a plus b. Now you have to kind of keep your mind about this. This is your linear term, the degree 1 term. This is your constant, all the way from negative backwards. And the coefficient of our degree 1 term is 5, and our constant is negative 19. So our equation is going to be the coefficient of x has to equal the coefficient of x, and we're told right off the bat that a has to equal 5. Then we have the constant, negative 4a plus b, has to equal the constant on the other side, negative 19. But in this case, we know that a is equal to 5, so this becomes negative 20. So we have negative 20 plus b is equal to negative 19. When we add the 20 across, we find that b is equal to 1. So this partial fractions becomes 5 over x minus 4 plus 1 over x minus 4 all squared, because a was equal to 5 and b was equal to 1. So the partial decomposition of this fraction becomes these two fractions. Alright, here's a more complex problem to partial fraction decompose. We have a quadratic on the top, and in the bottom it's actually a cubic. After you multiply x times x squared, you'll get an x cubed down here. So the setup is right. The power on the top is lower than the power on the bottom, degree, top to bottom. So the separation of this one is going to be a linear factor and a quadratic factor. And there's no way of breaking that down any further than x squared plus 2. So the linear factor is easier. That's just a over the linear factor. When we get to the quadratic factor, because the top has to be a degree less, we're going to get a linear factor in the top, bx plus c, over our x squared plus 2. So the previous examples just had an a and a b. This one has 3 variables. So that kind of leans into we're going to have 3 equations with 3 unknowns. Alright, so if we multiply through by the common denominator here, this x plus 2 and the x squared plus 2, it leaves the top alone on the left, so we'll get this. The x plus 2's are going to cancel, so you'll be left with the a on the top and the quadratic factor. The x squared plus 2 is going to cancel, so you're going to be left with a linear factor of x plus 2, but also this linear factor of bx plus c. So be careful, put the bx plus c in parentheses before you do anything else, because you're multiplying everything by this x plus 2. Alright, and then expand. So we're going to have x squared plus 7x plus 4 on the left, and then ax squared plus 2a, and then over here we're going to have to FOIL, so bx squared, 2bx. In the middle here we're going to get cx, and then the last we're going to get 2c. Alright, so we've expanded it all out, and the next step is collect like terms. And while I collect them, I'm going to factor at the same time. So let's see here. We have an x squared term here and an x squared term here. So I'm going to kick out the x squared and leave behind an a and a positive b. Alright, next up would be, let's do purple, the x terms. So there's only 2 of them, here and here. So if I kick out the common factor of x, that leaves behind 2b plus c. Only kick out the variables. If there's any other common factors, just leave them inside. And all that's left is the constant. So what's left for the constant is this 2a and back here the 2c. So we're going to have 2a plus 2c. So the green one should match up with the x squared on the other side. A little side note. If it was missing x squared, that means it was 0x squared, so then I would take a plus b and set it equal to 0. But in this case, the coefficient is 1, so I'm going to go a plus b is equal to 1. Alright. For the single x term, on this side it's a 7 in front of it. On this side it's 2b plus c. So I'm going to write 2b plus c must be equal to the coefficient of 7. And then lastly, we have this 2a plus 2c, which is our constant, and our constant on this side is just a positive 4. So 2a plus 2c has to equal that positive 4. Alright. Now all I have to do is figure out how to solve this. There's several different ways of doing it. One thing to notice is the first equation just has the a and the b. The second equation has the b and the c. And sadly, the third equation has the first one and the last one, the a and the c. So one way of doing this is to force 2 of the equations to have the same variable. For instance, maybe I want a and c as my main variables. So this one has a c, but it does have this b that I need to get rid of. So I'll take the first equation and I'll solve for b. So b is going to equal 1 minus a. Take that and substitute it in here. So we're going to go 2 times b plus c is equal to 7. The b is now equal to 1 minus a. So we're going to get 2 minus 2a plus c has to equal 7. And if I move the 2 across, I'm going to get negative 2a plus c is equal to 5. Now I have an equation in a and c that matches this equation over here with a and c, and even nicer, this one's a positive 2a and this one is a negative 2a. So I'll just move this into position underneath and use elimination. So negative 2a plus c is equal to 5. Add these two equations together. We'll get 3c is equal to 9, and c is equal to 3. So we found one of the variables so far. C equals 3. Now I can go and find an a and then find b. So take this one, I'm going to plug it into this one over here. You could have also plugged it into the red one up there. Either one's perfectly fine. So if I plug it in here, I'm going to get negative 2a plus c, which is 3, is equal to 5. If I subtract the 3 across, I'm going to get negative 2a is equal to 2. Therefore, a is going to equal negative 1. That gives me two of my variables, these two. And then to find b, I can take this one and bring it all the way back over here where there's a relationship between a and b, and say b is equal to 1 minus, and a is negative 1. And therefore b is equal to 2. And there's my a, b, and c. So if I plug it back in, this becomes a, negative 1 over the linear factor x plus 2, plus b, which is 2, x plus c, which is 3, over x squared plus 2. And there is the partial fraction decomposition of the original fraction. A nice breakdown version. Alright, for this example, I'm just going to make up one, which is bad because then they're not going to come up as nice whole number answers, more than likely. So I'm going to make it kind of simple for the top. 1 over x minus 2, x plus 3, x minus 4. Alright, so they're all linear factors, so it's a simple setup. It's going to be a over x minus 2. It's going to be b over x plus 3. And it's going to be c over x minus 4. Nice and linear. So when I go through and multiply by the common denominator, I'm going to get a 1 on this side is equal to, let's make the top a little bit messier. Use my eraser. Big. Let's change the top just a little bit, just to make it more interesting. Let's undo a little bit. Darn it. Erase it again. Let's make it x plus 1, or 2x plus 1. That's even more unique. There, that looks prettier. It just makes things horrible later on. So after we multiply through by the common denominator, we're going to get 2x plus 1 on this side is equal to, the x minus 2 will cancel, but that leaves two factors behind. So we're going to get a times x plus 3 and x minus 4. When we get to b, the x plus 3 is going to cancel, but that leaves you the other two factors. So you're going to have b times x minus 2 and x minus 4. And lastly, we'll get to the c. That's supposed to be a 4. The x minus 4s are going to cancel, and you're left with the other two factors. So it'll be c times x minus 2 and x plus 3. And you're thinking to yourself, oh my gosh, I have to expand all of this mess out. And generally, yeah, you probably would have to, unless I show you a neat little shortcut. And the shortcut is this. X is a variable. You can let it equal anything you want. So if I let it x equal, let's say, -3, then what's going to happen is wherever there's an x plus 3, that term is going to turn into 0. So it kills this entire c term, and it kills the entire a term, but it leaves behind just the b when x is equal to -3. So if x is equal to -3, you're going to get 2 times -3, which is -6, plus 1, which is -5, is equal to b times -5 times -7. That's coming from letting x equal -3 here and x equals -3 there. So that's a total of 35. Or if you're smart about it, you would just cancel the 5s. But if we make it 35, you get -5 is equal to positive 35b. Therefore, b must equal -1/7. So that's a quick way of finding the variables. And this trick works really well when they're linear factors. It doesn't work so well if there's repeated factors or if there's quadratic factors. But if they're just all linear factors, we can do this. All right, let's try another one. How about let x equal, and if you think about it, you just want to get rid of one of these. So I'm going to let x equal 4 for the next one. If I let x equal 4, that's 2 times 4, which is 8, plus 1 is 9. If it's a factor of 4, or the x minus 4 factor, it's gone, and it kills the b and the a term. So all you're left with is c. So we're going to get c times 4 minus 2, 4 plus 3. Did I do that right? 4 minus 2, 4 plus 3. Okay, so that's 14, and when we solve for c, we're going to get 9/14. Very quickly. All right, so there's one last one. Do it in red. We let x equal -3 and 4. That leaves this x minus 2 guy. So I'm going to let x equal 2. Now if I let x equal 2, 2 times 2 is 4, 4 plus 1 is 5, so the left-hand side is 5. Anywhere there's an x minus 2, the whole thing goes away because it'll be 0 times it. That leaves me the a term. And then if I plug in the 2 for the x, I'm going to get 2 plus 3 is 5, and 2 minus 4 is -2. So this will be 5 and -2. So that's -10, and if I divide it across, I'm going to get a equals -1/2. So the partial fraction decomposition of this, weirdly written, would be -1/2 over x minus 2. B is B is negative. -1/7 over x plus 3. And then c is positive, so plus 9/14 over x minus 4. Now there's better ways of writing this. For instance, this is -1/2, so you could write it as -1 over 2 times x minus 2. That's the more proper way. Or, if you really want to be fancy with it, you can go -1/2 times 1 over x minus 2. Either way is perfectly acceptable. This way is not super acceptable, but if you are in calculus, you're eventually going to just write it like that and do something to the 1 over x minus 2. So that's the shortcut version. It really only works with linear factors that do not repeat. So x minus 2, x plus 3, x minus 4. No squares up here. It does kind of work for the square, but you still have to expand.